Okay.
Tuck in on that a little bit. There you go. There you go. Nice. Perfect.
Hi.
All right, holler if y'all need anything, okay?
Okay. So, hi Logan. Hi Ryan.
Hello.
Did you get my email yesterday, Logan?
Me, yes.
I haven't checked my email. I'm sorry.
Okay. How's your computer? Did you get that fixed?
It is good. It is good.
Good.
Like I just had to replace the battery. Like they had to like take apart the computer since it doesn't have like a direct slot and stuff like that.
Okay.
And like put it back in.
I see. Okay. Did you ever? I never got your homework from last time. You had said in a day you would send it, and never got it.
Oh.
Okay.
I'll have that in by the end of the day today. I forgot.
Okay.
Yeah.
Yeah, I thought so. All right, and I was behind, and Ryan, I apologize for not making an appointment. I didn't check till yesterday. I was
fine.
I got busy. How are you guys?
Good.
Good.
Yeah. Kind of tired.
Kind of tired.
Okay.
Okay. Are you going to hear from colleges pretty soon? Is that was the time or something? Or have you heard?
I've heard pretty much back from all of them that I applied to.
How'd you do? Or where did you get in? I guess is the question.
I got into TCU, St. John's, and Pepperdine. And those are like the first wave of applications I did, and then I did like 4 more, and I'm pretty sure I got into all of them.
Oh. Okay. Then you got to choose. That's the other end. What about you, Logan?
I got in to a couple, but I'm waiting to hear back from my top choice. I'm gonna hear it at 4 o'clock today. So.
Oh, okay. Pretty exciting.
Yeah. So. I don't really know yet. Yeah.
Yeah. Okay. A little nerve-wracking. I know it's not. It's always a little. It's hard time a little bit, but exciting too. Okay, so Ryan, I read. Oh, I also didn't get your journal, Logan. That's it. All right, just when you get a chance. So Ryan, you had questions. So that's what we're gonna do today, and I didn't answer them before, but we'll get to them right now. So, what's the best way for us to do this? I have what you sent me, and we can show that and talk about it, and you can take notes. I can show it, or you can show it. What do you think would work better?
I think either way, because I just have the PDF file that I sent you of that homework, and you have the exact same file.
Yeah. Okay. Yeah. All right, I'll show it and we'll talk. So you should have some paper, since you did it on paper, and Logan, you should have some paper too, to take some notes if you need to.
Yeah.
On how this works. So I'm going to share my screen. Yeah, that one. Okay, sharing the right one. Oh, and I want constant presence. Active speaker. Yeah. All right, let me stop. I'm going to stop sharing for a minute and get the, there we go, and get the constant presence that I want. And then I have to say something to make that happen. Apply layout to all participants. That's what I didn't do. There. Okay, that's what I hadn't done before. And now I can go here and share entire screen. Okay. I see you guys too. Okay. Okay. I wonder if I can move this over. Yeah, I can. Oh, that's nice. That's nice. Oh, but then I get an echo. Do I get an echo here too? No. All right. So I'll leave it here. All right. Oh, I get an echo now too. So what do I do? Silent, mute. No. I don't know. I don't know why I'm getting an echo, but I am. Now I'm not. All right. So this is actually this is the transforming graphs part, and you corrected number 6, Brian, and you did a pretty good job. I just made one comment at the end. So let's go through it for Ryan too. But I also wanted you to do the same, I think. Let me look at the assignment. Yeah.
Oh.
No, you did exactly what I asked. But I did say include a graph. That you didn't do. Include a graph that shows your starting function. That would have, I made a picture, but I wanted you to also. Include a graph that shows your starting function, the desired asymptote, dashed line, and the desired points. You can use GeoGebra and copy and paste, or draw on graph paper, scan, insert, either way. So that's, I'm not answering that. Sorry. Oh, Jesus. It'll go into the, you know what? Energy recovery, I'm not interested in. Let me just get rid of that. Okay.
I started, I used GeoGebra for that, and I thought I included another file, but let me check if I did or not.
All right. Sorry, I can't do anything about this. It's going to roll over into the voicemail because I'm not answering. Okay.
Hi, this is Lou. To leave a message for Diana, press 2 now. To leave a message for Lou, press 1.
There. Okay. Turn the volume down.
Mr. Douglas?
Yeah.
If you scroll down to the very last page, I included a GeoGebra file.
Oh.
GeoGebra graph.
Got it. I didn't go far enough. You did it. Thank you. I'm sorry. Yes.
It's easy to miss.
Okay. Perfect.
Yeah. So I started with
yeah. So let's go back.
Yeah.
Okay. All right. So you followed the steps, which was, where's my, there. So you followed the steps, which was good. You said start with y equals 2 to the minus x. It has a y-intercept at 0, 1, and an asymptote at y equals 0, and the graph is decreasing. And then you described, step 2 was to describe the transformations. So the desired graph has, I'd like to sort of see it both, but okay, the desired graph has its y-intercept at 12, 15. And so what you did was let's go down to the graph now. Yeah, so you wanted to move the axes. So these dashed lines are your new axes.
Yes.
Right. So you wanted to translate it over there. And then the y-intercept now is 5 because it's from 10 to 15.
Yeah.
Right? Okay.
Uh-huh.
So now we go back here. Okay, so that's what you said here. If we compare the new y-intercept, so you wanted a vertical stretch of 5 because the vertical stretch of 2 to the minus, well, excuse me, the y-intercept of 2 to the minus x is 1, and you wanted it to be 5. So you wanted a vertical stretch with factor 5. And then, so instead of yeah, okay, I would say with factor 5, but a 5. So to get the 630, which is the other point, on the old graph, we need a horizontal stretch. And then you said 30 minus 10, so that's from the asymptote, is a vertical of 20. And 20 divided by 5 is 4. So this gets us the y-coordinate for that corresponding point. And negative 2, 4 is the corresponding point. So let's go down here. Okay, so explain that.
So if you on the first graph, the graph farthest to the left, which is the original one, could you actually scroll up a bit to include the 630?
Yeah.
Well, we had this that coordinate, the 630. So that's what you gave us, but we didn't have a corresponding point on the original graph that we were starting with. So I tried to find the y coordinate for the on the original graph of a corresponding point. Since we used a vertical stretch to get to the new graph, I subtracted the shift or the vertical shift that we had, and divided that by the vertical stretch to get a value for the y value of the corresponding point.
Okay. So 20 divided by 5 is 4. So that's how you got this 4.
Yeah.
Okay.
And yeah. And then I went to my calculator, and I saw if any points on the original graph, so 2 to the negative x, if any of them had a y value of 4. And I think negative 2 came up.
Yes.
For the x value, so I marked that.
Okay. Yeah, so this is your corresponding point that you want. Okay. And so, yeah, so let me see.
And then I could find the horizontal stretch from that.
Okay. So then you said to get negative 2 to correspond to the 6 on the x-axis, you take the 6 and divide by negative 2 and get a horizontal stretch of 3. So I see. So the 6 you're talking about is not the 6 coordinate, it's the distance from 12 to 6.
Yes.
Okay. So that distance here is 6, but the distance here, the x distance is 2, from 0 to negative 2. So you wanted a horizontal stretch with factor 3 to stretch this out so it has the same horizontal movement, right?
Yes.
Okay. All right. So that's where you get a horizontal stretch of 3. And so just the last thing that would have been good is the order is important. So what you're doing is you're doing the stretches first. So you're taking this graph and you're having a horizontal stretch of 3 and a vertical stretch of 5, and then you're translating it over here.
Okay.
If you did it the other way around, things would be different. I want you to realize that. So, for example, if you took this graph and moved it here, so that the asymptote,
Okay.
right? And then,
Yeah.
you see that?
Mm-hmm.
And then
It
if
would,
you did a vertical stretch, the asymptote would change. That's what I want you to see. See, if you moved it over here, just move the graph first over here,
yes.
and you have a y equals 10 as the asymptote. But now, if you did the vertical stretch, everything would go with factor vertical is 5, with factor 5, and including these points here would go 5 times as far away from the x-axis.
Okay, yeah. I see.
So that's why you have to do the stretches first, which you did, but you weren't completely aware of that. So that's why you had to do the stretches first and then the shifts. And so your transformation is exactly that. When you took the x and you stretched, when you say 3x plus 12, what you're doing is you're taking the x and you're first multiplying it, you're first doing the stretch, and then you're shifting.
Okay.
If it was the other way around, you would say, you would have parentheses, x plus 3, and parentheses, x plus, what is it? What is the horizontal? Horizontal is 12, yeah. Parentheses x plus 12, and then the 3. Let me get to the right place. Yeah, you would have the x plus 12 in parentheses, which is the shift first. Sorry, and then the stretch. So when you say 3x plus 12, what's happening is the stretch is happening first, and then the shift.
Okay.
Okay, and the same 5y plus 10 is the stretch is happening first, and then the shift, which is what you want. Okay, and then you found the inverse, which is here, and you went in reverse order. You have 3x plus 12. The last thing being done is plus 12, so you subtracted the 12. And then the first thing being done is times 3, so you undid that by dividing by 3. And the same here. So that's the inverse. And then we substitute into y equals 2 to the minus x, and you get this, which is the correct equation. And then you multiplied by 5 and added 10, and you got to here, which is good. But my little comment is, this is correct. Well done. That's the first thing I say. But it should be simplified. So what you do is you break up the exponent into 2 terms, right? This is minus x over 3 plus 12 over 3.
Okay, yes.
And then you using a law of exponents, and then you use a law of exponents and combine the numerical part with a 5. So it's 2 to the minus x over 3 times 2 to the 4th. 2 to the 4th is numerical. So you figure out what 2 to the 4th is, multiply that by 5, and you get a number. Okay. So that form is a little bit nicer, but this is completely correct and good. Okay, Logan,
Okay.
you clear on that?
Yeah.
Okay. So what I'd like you to do, since we've gone over this one, is to, instead of doing 6, if you haven't done this yet, then it would be good to do that with 5, all the steps. Okay?
Okay.
Yeah. To see how that works. Okay. And, just to get used to doing all the steps. All right. And that's that one. Close that. Now, this is where, Ryan, this is where you had some questions.
Yes.
Right? Okay. So let's do this slowly. Okay. So, we're using, all right. So we're using complex numbers to compute the image of the point AB under the following isometries. All right, so translation by vector VW. So, so this is the example. So we take A plus BI. All right. So this is this has a mistake. I have to tell Henry what I'm seeing today. This should be plus, right? Yeah, we're adding. So it's A plus BI plus V plus WI. That's what it should be. Equals A plus V plus B plus WI. So the image is A plus B and A plus V and B plus W. So this is not multiplication. This should be an addition here. Okay?
Okay, that clears up. Yeah. Okay.
So that's a mistake. Sorry about that. I'll fix that. Now that I have a Word version. It was originally in as a PDF, that I got it. All right. Now translation by a vector with polar coordinates r theta. So for translation, we would like to have, so this also should be plus here between these two. So translation by vector with polar coordinates r theta, you want to make it into rectangular coordinates because translation works much better with rectangular coordinates. So you have A plus BI, and then the rectangular coordinate, the rectangular form is r cos theta plus r sine theta times I. That's right, and you're adding. So adding these two is A plus r cos theta, and then BI plus r sine theta I here, and then you factored out the I. And so the image is, so this is the new x coordinate, and this is the new y coordinate, so you put it in coordinate form, and that's the image, and that's fine. Okay, now we want to rotate by theta degrees around the origin. So now you multiply, because when you multiply, the amplitude is the stretch factor, is the dilation from the origin, and the angle, the argument, is the rotation. So we want the amplitude to be 1, because we don't want to change the distance from the origin. So r is 1, so it's 1 times cosine theta plus I sine theta. That's fine. And then you multiply these, which you did here, but you made a little mistake. And the little mistake is right here. The last term should be b cosine theta, not b sine theta, because that's the I term here, right? So you have a sine theta, that's right, times I, and then b cosine theta times I. So this should be cosine here.
Okay.
Okay? But other than that, it's fine. Now we started having a little more difficulty. So rotation by theta degrees around the point PQ. And what you did here...
Oh, okay. So I did that wrong because P and Q are not supposed to be the stretches.
Yeah.
It's just the starting point. Okay.
Yes. So we need a plan. We know how to rotate around the origin, but we don't know how to rotate around PQ.
Yeah.
So what's our plan? What are we going to do? So this is a little tricky, and it foreshadows this 3-step thing that we get down to here.
Oh, would we just move? Would we subtract? Oh, we would subtract from A plus BI, the PQ,
Yes.
coordinates, and then we'd rotate and then add them back on.
Yes.
Okay.
That's exactly right. So that's what I said here. No, you confused rectangular and polar. So we need to translate AB back to the origin, giving A minus B, A minus P, B minus Q. That's right. We translate it back to the origin. Then we rotate by theta. So we multiply by cosine theta plus I sine theta as before. And then finally, we have to translate back by PQ. And this foreshadows the three-step method that comes later.
So we move it, or we move the point back to the origin with PQ, subtracting that. Then we rotate using C, or the method in C, and then we just subtract AB, or the PQ from the new coordinates.
Then we add PQ back, because we want to go from 0 to PQ. First, we want to go from PQ to 0. So that translation is minus P minus Q. So it becomes A minus P plus parentheses B minus Q times I. Okay? And then that gets multiplied by cosine theta plus I sine theta. So you have to multiply that carefully.
Mm-hmm.
All right? And then you get something plus, V plus WI, whatever that is. And then you have to add P plus QI to that to get it back. Okay? So it's a subtraction of P plus QI, basically. You're subtracting P plus QI, then you're rotating by multiplying by cosine theta plus I sine theta, and then you're adding P plus QI to get back.
Okay.
Okay?
That makes a lot of sense.
Okay, good. All right, and then this part is fine. So you have the image of AB after reflection is A minus B, that's right, in reflection the x-axis. So the image of A plus BI after reflection is A minus BI. That's called the conjugate. And in GeoGebra, it knows conjugate. It doesn't do a lot of complex stuff. So you can never get the axes, the y-axis, to be labeled with i's. That you can't do that yet. Maybe they will at some point. But if you say conjugate of parentheses A plus BI, then it will give you the conjugate. Okay, so now here's the three-step method. So we use the same idea with reflection. So we'll find the image of AB under reflection in a line y equals mx. Okay? So we have to put it in. We don't know how to reflect over the line y equals mx, but we do know how to reflect over the axes, over the x-axis in particular. Or over the y-axis, but we picked the x. So we're going to rotate so that the line lies on the x-axis. Then we'll reflect across the x-axis and rotate back. Because this time, instead of last time, we translated and then rotated and then translated back. This time, instead of translating, we're rotating, and the major thing is reflection instead of rotation. So it's similar, but the major thing is in the middle. And this time we want a reflection, so the reflection is in the middle. But in order to make it convenient to reflect, we have to rotate first to get the y equals mx to lie on the x-axis. Then we do the reflection, and then we rotate back.
Okay. And after we do the first rotation, when we're reflecting it,
yeah,
are we just switching the signs of the second
Yes.
coordinate or
Yeah.
of the okay?
Yeah, that's right. Reflecting over the x-axis is easy. That's why it's a plus bi becomes a minus bi. That's a simple reflection. Yeah. So in this case, the reflection part in the middle. In the previous case, the rotation was in the middle, and that was hard. We had to multiply by cosine theta plus I sine theta. In this case, the reflection is in the middle, and the translation, getting it in the right place, was easy, and doing the rotation was hard. In this case, getting it to the right place is hard, but the reflection is actually quite easy. So it's kind of reversed.
Okay. So rotating is just hard.
Yeah, rotating is hard. You have to multiply. That's right. Okay. So we want the angle between y equals 2x and the x-axis, and you use the difference formula, which works, and you got the right answer, but I don't think we need it. I mean, we don't need the tan of a difference formula when beta equals 0. We could just go right to inverse tan of 2.
Okay.
Right? Yeah. Because the tangent is 2. You know that right away. So inverse tan of 2 gives you right here 63.4 degrees. Right.
Okay.
Okay, and then we say, I'm sorry, we're still on that first one. So we're still on this. What is the angle? You did that. What is the angle? And now we carry the rest of it. We have to say, what is the reflection of the point 32 across the line with equation y equals 2x? Okay. So here's what happened here. So 63.4 degrees is the angle. So we have to rotate by minus 63.4 degrees. And what you did was put the minus sign in front.
Yes. I actually corrected the that first part underneath. Where the beginning of the second page. I tried to correct it.
I missed that. I'm sorry. Okay. Jeez. Okay. So that's the second time that I didn't go far enough. But you need to tell me also. So cross out that first part.
Okay.
So that I know not to look at it.
Sorry about that.
Okay. All right. So I'm sorry too. Okay. So yes. So this is correct now. Yes, this is correct. So you have, except what I would have done here, though, at this point, well, it's okay. I mean, do you know the, instead of carrying that minus all the way through, do you know the rules for, cosine of minus 63.4? What is that the same as? Cosine of a negative value from your point of view. So cosine of an angle in the fourth quadrant, how does that relate to cosine of an angle in the first quadrant with the same rotation from the x-axis?
Isn't it just the same?
It is the same. Wait. So cosine of minus 63.4 degrees is the same as cosine of 63.4.
Okay.
Right. Now, what about the sine? What happens to the y-coordinate when you go the other way?
I think those are opposites, though. I think it's different for that. So. Yeah, I think it's different for there, though.
Yes.
Negative is different.
Yes, they're opposites. That's right. So sine of minus 63.4 minus sine of 63.4 degrees. That's right. So the cosine stays the same and the sign changes. Anyway, this is correct. So now what you did is you multiplied, so 3 cosine that, that's right, plus 3 sine this times I, that's right, plus 2 cosine this times I, that's right, minus 2, why the minus sign here? Oh, I see. Because you're doing the i's. Got it. Okay, so it's minus 2I times this, so I squared is minus 1. So it's minus 2 sine, right. Okay, so this is correct. Okay. And then...
right there, I converted it into coordinates.
Yeah, coordinates. Okay. So there are your coordinates. I see. That's right. So this is a real part. So you have 3 this minus 2. Yeah. Okay. And then 3 sine this plus 2 cosine. Right. Okay. And it's minus 63.4 degrees again. Yeah. Okay. Then you reflect it by changing the signs of the y's. So this is minus and this is minus because they were plus before. That's correct. And then you want to rotate back. That's right. So you want to take this, and now you put it back into the I form, A plus BI form, right? So it's this, yeah. Minus, yeah, because it's this one. Minus 3, oh, I see. This whole thing is in parentheses. Okay. Minus this whole thing times I. That's right. Times cosine, and this time you want to do a plus. That's right. Cosine 63.4 plus, yes, that's correct. And now you said not even close at the end. I think it would have been easier to, because you're on the right, you're right here. I mean, this is fine, but since it's so complicated, if you had changed this into cosine of 63.4 degrees and changed this into, sine of minus 63.4 is the same as minus sine of 63.4, then you'd have the same angle when you multiply, and you would have gotten sine squareds and cosine squareds, and that might have simplified. But I'm sorry, go ahead.
The reason why I put not even close is because I use my calculator at this point to try to multiply that and try to get actual points.
Yeah.
With, once I got to that part, to the very end, and I assigned certain values to the I assigned like theta to 63 or negative 63.4, so then I could just plug it in like I did 2 lines up, and
okay.
I'm not sure what the actual answer is, but
right. Another thing to do is to use the values instead of keeping the cosine of minus 63.4. Is just find out what that value is, and
okay,
and you can store those values, so you don't lose the precision if you want to. If you have a graphing calculator, something that'll store those values, then
that's what I did in those last 2 lines when I put in x plus bi multiplied by the cosine theta plus sine theta I. And once I funneled it down to that last coordinate of x cosine theta minus b sine theta, I used the values. I actually stored values for x and b, I came up with 3, negative 2, which I think is what we began with.
I see. Okay, let me try 2 things here. First, so I'll just talk this through, and you can write, and we'll see if we're on the same page. So first, let's just make that change that I talked about and see if that makes some simplification. So,
Okay.
I'm going to write 3 cosine 63.4 degrees. And then it would be plus 2 sine 63.4 degrees. 2 sine 63.4 degrees. This may be too messy. So that's the first one. And then the I part, you have minus that whole thing. So I'd rather do a plus and just get that. So plus and then parentheses minus 3 cosine 63.4 degrees. And then, is it cosine both times? Let me check that.
For which point? Which part?
The I part. I'm looking at the I part here. Because you went back and forth. You went to. Okay, here's the I part here. So, yeah, one is. See, in the I part here, one is sine and one is sine and one is cosine.
Can you put your cursor over where you are in the work?
Yes, good point. Here, this part here.
Okay.
This is sine, and this is the A part, A plus BI. The A part is cosine and sine, right? And the B part is sine and then cosine.
Yeah. And
but here you have cosine both times in the B part, right?
Oh. That might be why.
Yeah. I think that's the problem.
Okay. Well, okay. So I was on the right track except for that mistake.
Yes.
Okay.
Yes. And at this point, I'm thinking that keeping that 63.4 degrees all over the place is just so complicated because you have all those terms. So even if you did get something nice with with sine squared and cosine squared and stuff, it's just not worth it.
Okay.
So I would take this point here and just make it a number.
Okay.
Yeah, that's much easier. So some number plus like what you did here with the x and y, except I would do it earlier. Yeah.
Okay.
Just make it number, and then it's much easier. And then use the same thing with a cosine plus I sine theta, just a number. So you'll have something of the form x plus and a plus bi times c plus di with numbers. Okay. And then you can you can store your a, b, and your c and your d, and then you get if you have a plus bi in general times c plus di, then the real part is AC minus BD, and then the complex part is BC plus AD times I. So if you have your A, B, C, D stored, then it's easy to get the real part and the imaginary part of the product.
Okay, yeah, that's way easier.
Okay. All right. So now let's just go to the last one. And yeah, you get a wow. So at least 6 anyway. And so now this is actually, this gives you a check sort of on this thing. Because reflecting 3, 2 over the line y equals x, we know the answer is 2, 3. So Now we check whether the three-step method gives us the right answer. And what I would do here is, instead of keeping the cosine pi over 4 and sine pi over 4, you know what those are, I hope.
Yeah.
Right? What is cosine of pi over 4?
Isn't that pi? I'm not sure. I need to look at the unit circles.
It does have
so do that. Draw. It's an isosceles right triangle.
It's like
That's 145.
Radical 2 over 2.
Yeah.
Yeah, radical 2 over 2.
That's correct, Logan. So both cosine of pi over 4 and sine of pi over 4 are radical 2 over 2. That's right. So that makes it a whole lot easier.
Yeah.
So you substitute those things, and then it should work out without having to use a calculator, because radical 2 over 2, things multiply nicely.
Okay.
Or it's interesting. I mean, there's almost no. The reason we rationalize denominators. Do you know the reason for that?
Because we didn't have calculators way back when, so
that's right. That's right. That's the only reason. So these days, that's kind of a silly reason. So you can keep it as 1 over root 2, and that actually makes the calculations easier. But either way, it'll work out.
Okay, I'll go back and do that.
Okay, so that's the check for that. And then now, so just to go over the strategy here. Excuse me.
With this one,
yeah.
What I wanted to do with this one was since I wanted to go to or translate it over a y-axis, or a y-axis, but or I don't. Never mind. I don't know.
Okay.
So I wasn't sure how to make it a 5-step process, I guess.
Okay. Well, let me talk you through that.
Okay.
So how does this y equals 2x plus 5 differ from the y equals 2x?
It's shifted up 5.
Yeah, that's right.
So we have to combine. I think part D.
Yeah, whatever it is, those two processes. That's right. Okay. So you have to first translate it down, right? And now this part, the part of reflecting over y equals 2x, you've already done. Those 3 steps were done. So you would do those same steps. You translate it down so that now it's y equals 2x. Now you rotate it so that y equals 2x lies on the x-axis. Then you reflect across the x-axis just by the conjugate. Now you have to put it back. So you rotate back so it has the right slope of 2. And then you translate back up 5 units to get to where you want to be.
Okay. Okay.
But those awful middle 3 steps you've already done. That's the good news.
I definitely did not translate it. I did not see that part.
Okay.
I didn't make the connection at that point.
Okay. Okay. So, the last thing I want to say here, and then I'm behind, and I'll explain what I need to do. So, now, it says on the bottom, assuming you can do all that, and so, yeah, you should go back and correct that. And since there's so much to do here, I haven't made, was going to make the homework for, these last 2 times, because I said there'd be 3 times as much homework. I haven't done that yet, and I'm going to do it today. I have a meeting at an hour after class ends, and that'll last about 2 hours. But the rest of the day will be devoted to this. So I'll make homework assignments, which I already have a pretty good idea what they are. But I won't make them too long, because you'll have a fair amount of work to do here.
Okay.
And then this is what's coming up, which is the key feature of what we're doing here, and that is you can now compute the results of any isometry. Okay. However, this method has shortcomings, as you see. It's tricky to keep track of the parentheses and the order of operations. It's inconvenient when calculating the image of a polygon, as the calculation has to be done for each vertex. Oh my God. Right? And it doesn't generalize to 3 dimensions. Because, complex numbers are numbers in the complex plane, and there's no 3-dimensional kind of thing. So the key thing is all these concerns are addressed using matrices. So that's one of the key purposes of matrices, not just, in textbooks they say, solving systems. Okay, yeah, that helps. But it's basically the idea of keeping track of lots of numbers. That's what they're for. And you have all these calculations going all over the place, but they're systematic calculations. You kind of know what to do. It's just a pain in the neck to do it. And so that's what matrices are for, is they keep track of all these numbers in a simple way, and they're useful for transformations because there are matrices corresponding to these transformations if you do it right. And so that's what we'll do. And then, first of all, it's easier to keep track, and secondly, you can tell a computer to do it, which is the key idea, right? Once you know exactly what to do, and you have these nice little forms to keep track, then you tell a computer to do it. And so that's what we'll learn next, and that's the basis of computer animation. All the computer animations are done by matrix calculations of geometric transformations. When you see, I had my granddaughter this weekend, and she's we had her at our house, which is nice. She lives in San Francisco, and she's almost 11. And we took her to see Cinderella. And she's kind of too old for Cinderella in a way if it was just Cinderella. But it's really well done. It's a Disney movie. And the animation... have you seen it?
Is it the new one or the old?
It's new. Oh, new. It just came out. And the animation is awesome. It's really good. And so, for example, when she's running back to her house at midnight, because it's just, the clock is striking, and the animals have been turned into, the pumpkin has become big, and then the goose has become the footman, the driver, and then a lizard has become the guy who rides on the back. I forget all the names. The assistants of various sorts who are riding in the carriage. And so it gradually turns back, and you can, instead of just, being all at once, little parts of them, the guy who's in the back suddenly has a tail again, like a lizard, a little part of it, and then the goose suddenly has a beak, and then he has so they really did that well. It's and you can see it gradually go back. So that's just one example. And then the gowns that suddenly she looks like with a great gown. So the animation is terrific, and that's how they do it. They do it using matrices, and they do it using smoothing. I saw a talk by someone who worked at Pixar before Disney bought it. Oh, still, they Disney still uses. Fortunately, they didn't ruin, everything in Pixar. Pixar is awesome, and it was right here. It's where I live, actually. The Pixar Studios in Emeryville, like 2 miles away. But but he gave a talk about how they smooth it out, basically. So you have these particular points that you keep track of, and then there's a smoothing technique where you can tell it to join the 2 points with a smooth curve that's not too hard, and then you move it. If you want to move, you basically have the starting position where you're going to be, and then the ending position, and the smoothing technique allows you to go from one to the other in a nice, for several steps that are, that look nice. So that's math. All that stuff has to do with using math to make this animation, and it's all transformations, three-dimensional transformations. So that's where this stuff comes in. Okay, so that's the story on this, and I think we're basically done. So the triangle thing with the smooth moves, that you didn't have any trouble with, and that seemed relatively straightforward. So I'll have you finish that, and then we'll talk about the group, and then the other thing I think I'm going to assign is you said you didn't know much about the golden section or the golden ratio, and I have a really nice activity with a pentagram that I had done. Actually, I got it published in there's a magazine called The Mathematics Teacher, which is for math teachers, and there are actually 3 magazines: one for high school, one for middle school, and one for elementary. And the high school one is called The Math Teacher, and I got it published as an activity in that a number of years ago. So it's good, and it has a lot of transformations and interesting things in it that are surprising. I mean, it's a wonderful number, just like pi is, and so and e, those terrific numbers that come up. So I'll include that, I think, and just keep going with matrices. So that'll be the next thing, is some activities involving matrices to get us started on that. But I won't introduce any brand new thing until next week, until the following week, when Walter's back from China.
Okay.
Okay. So you got your questions answered, Ryan?
Yes.
Okay. And Logan, you got a good idea what to do?
Yeah.
All right, you guys. So don't forget to do your work today, Logan. Get it to me, okay? Including your journal. Yeah. All right, and you have several back journals to do. Okay. Have a good day.
Thank you.
Take care.
You too.
Thank you.
Bye.
You're welcome. Bye.